This video is about DIAC. DIAC means diode for alternating current. Like triac, it is also a bidirectional semiconductor switch that can be turned on in both forward and reverse direction. The figure represents the symbol of the DIAC. You can observe the two diodes are parallel and opposite to each other. Unlike triac, which had three terminals, DIAC has only two terminals. Since DIAC switches both positive and negative half cycle of the AC waveform, the two terminals of DIAC are not anode and cathode. They are just anode 1 and anode 2, that is main terminal 1 and main terminal 2. And you can observe there is no gate terminal in DIAC. So understand that the voltage across MT1 and MT2 is the voltage that switches the device on and off. This figure shows the construction of the DIAC. It has a 5-layered structure, and you can observe the combination of both positive and negative layers in the layers closer to the terminals. This helps the layer that has the polarity similar to the voltage to get activated, thus helping the DIAC in operation in both the directions. And note that the structure of the DIAC is symmetrical, unlike triac, where triac has 6 doping regions and the structure of the triac is asymmetrical. Now, let us understand the working of this device. During positive half cycle, that is when MT1 is positive with respect to MT2, then the layer, that is P1 layer near MT1, will be activated, making the junctions P1 N2 forward biased, P2 N3 forward biased, and P2 N2 reverse biased. But when this applied voltage crosses the breakover voltage, that is when the avalanche breakdown occurs, the reverse bias at P2 N2 junction reduces, and so the device conducts with the current path P1 N2 P2 N3. So in this way the device conducts for the positive half cycle of the AC waveform. During the negative half cycle, that is when MT2 is positive with respect to MT1, then the P2 layer near MT2 will get activated, making the junctions P2 N2 forward biased, P2 N2 P1 reverse biased, P1 N1 forward biased. With the reverse bias at P1 N2 junction, initially the device will be off, but when voltage crosses the breakover voltage, the device conducts with the current path P2 N2 P1 N1. This is how the conduction is possible in DIAC in both the directions. Now, let us put the entire understanding of the working on the graph and draw the VI characteristics of the DIAC. You can observe the device will be in the blocking state until the breakover voltage is applied. When the voltage crosses the breakover voltage, the device gets conducted. When voltage crosses the breakover voltage, reverse bias gets reduced, means the resistance at the junction decreases, causing the current to increase and voltage to decrease. So, a negative resistance characteristics is exhibited by the DIAC after the breakover voltage, and the device will be in conduction until the current is greater than the holding current. When the current drops below the holding current, then the device gets off. Holding current means the minimum current required to keep the device on. The curves in the fourth quadrant represents the VI characteristics for the negative half cycle. And note that a small leakage current is shown in the VI characteristics because of a reverse bias junction initially. Till now, we have studied the DIAC, thinking its application as a switch, because switching needs proper control. But DIAC cannot be used as a switch. Because there is no gate terminal for the DIAC, we cannot say when the DIAC will get turned on when it crosses the breakover voltage. and so we can't predict when the DIAC will get triggered. And not only this, because there is no control signal in the DIAC, we can't make the device off whenever we want to, like a switch. The device goes into non-conduction only when the current drops to level less than the holding current. So, because of the lack of the control, the DIAC cannot be used as a switch. Instead, it can be used to provide sharp pulses, that is, to trigger the other devices like SCR, TRIAC, etc. And note that the TRIAC is always used along with the DIAC because of the asymmetrical switching of the TRIAC. You can refer the previous video and observe that the TRIAC has the asymmetrical structure, which means the doping concentrations and the regions that involve in conduction are different for both the half cycles. Because of this asymmetry, switching of the triac does not happen exactly at the same points for both positive and negative half cycles. Because of this, unwanted harmonics are introduced. And also the current received by the load in the two half cycles is different. So in order to avoid this asymmetrical switching, triac is always used along with the DIAC. So the DIAC generates a sharp pulse, that is a trigger pulse to the gate terminal of the triac, such that the switching is symmetrical in both positive and negative half cycle, which means DIAC ensures the balanced conduction of current in both half cycles of the AC waveform. This concludes the topic of DIAC. If you like the video, subscribe to my channel, like and share the video. Kindly help me to help you.